Good afternoon. Welcome to the SAME Resilience Community of Interest webinar. This webinar is called Using Simulation to Understand and Improve Resilience. A few housekeeping notes. I'm Karen Offringa from SAME, and a few housekeeping notes. Please mute your phones. Submit, if you have any written questions, please submit them in the Q&A tab on the right side of the PowerPoint slides. And we will get to those at the end of the presentation. During the presentation, all participants, everybody will be in a listen-only mode. The PDH certificate, which is one PDH, will be emailed to everybody after this session. And the webinar is being recorded and will be posted to our archived webinars page in about 1 to 2 weeks after the session. We're going to start with a quick poll just to see who all is on the line. So if you could answer just who you represent, and we'll look at those results real quick. So let's see. So it looks like the majority of our participants or attendees are from medium and large businesses, which represents about 70%. And then a few people from small business and civilian at government agency and active duty military. Great. Our speaker today is Stephen Bourne. Stephen Bourne is a professional engineer, climate scientist, and project director and fellow at Atkins, a global engineering consultancy. Mr. Bourne has 20 years of experience in developing decision support systems to help with shared vision planning. Some examples include tools to help plan out ice road routes to minimize environmental impact on the North Shore slope of Alaska. Also helping residents of Lake Tahoe plan out sediment control plans to keep the lake clean, as well as forecasting asset life cycle costs for the $14 billion South Florida Water Management District Stormwater Control System. Mr. Bourne's latest work is the Atkins Simulator Suite, which includes City Simulator and Seaport Simulator, two tools that use simulation to better understand climate change impacts and how to get the best return on investment with mitigation and adaptation approaches. And a few fun facts about Mr. Bourne. He was born in England, grew up in Bermuda, and became a U.S. citizen just a few years ago. He's already has visited 47 states, mostly by road trip, and his eldest daughter graduated from Georgia State University just this past December. So with no further wait, I will go ahead and let Mr. Bourne take over.
Okay, thank you, Karen. And I should note that while I became a U.S. citizen in 2019, I've actually been in the U.S. since 1993, so I had a long time to do those 47 road trips. Let's jump into the presentation. Using simulation to understand and improve resilience. Back in about 2012, Atkins did an initiative called future-proofing cities. And part of that initiative was to come up with tools to understand resilience and help our clients predict resilience, understand how they could improve resilience, and so on. And the city simulator tool I'm going to present today is essentially what came out of that initiative. When we were thinking about it in 2012, we were thinking, okay, let's build a tool here and let's think about what its requirements are. And so we started with the chart like this, sort of on the back of an envelope. We said, well, what is a resilient city versus an unresilient city? How do you measure resilience? And we threw this up as a chart. We said, well, we probably want to look at over time what's happening to the city. And we probably want to understand, one of our first sort of light bulb moments was we don't really want to measure resilience On the y-axis, we want to measure something like how well the city is doing. City Prosperity Index, that's an example. That's a UN specified index. But there's lots of ways you can measure how well a city is doing. But resilience, we thought, is that the ability to, if something happens to the city, some sort of shock event, it's its ability to recover and continue doing well. So that's really the metric we want to measure, is how well is the city doing. Our thought process, we first thought about, okay, during business as usual times, a resilient city is probably going to be more prepared, and therefore it'll improve in terms of its prosperity and other metrics like that, um, at a higher rate than an unresilient city, simply because it's sort of paying attention to itself and managing itself. When a natural disaster occurs, you expect the resilient city to, take an impact just like the unresilient city one, but it would take less of an impact because its infrastructure is more robust. Um, and then what's really important here, the true difference between the two is how long they take to recover after that natural disaster or other kind of shock event occurs. A resilient city, it's going to recover pretty quickly and get back to the level of prosperity it was at before the disaster. The unresilient one is going to take a long time. And this is not an unrealistic depiction here. 20 years to recover from a major disaster. Think about a place like Puerto Rico, where we often do work in resilience. They were in a economic downturn prior to Hurricane Maria hitting in 2017, and it is projected it's going to take a couple of decades for them to return to that level of prosperity. So, our thought was, let's create a tool that can actually create this chart. That's what we're looking to do. Um, we were, doing a software development process, so we have to write down requirements. And these are some of the high-level requirements we came up with. First, let's capture interacting systems. We at Atkins, we're very much a flood model focused company. We work for FEMA a lot. That's one of our key clients, and we do a lot of flood modeling for them. But we said let's sort of expand our view here and look at the economy, people, infrastructure, natural systems. How are they all being impacted by these climate stressors? And when they are impacted, what is the interaction between these systems? If we can understand that better, perhaps we can understand better how to make them more resilient. Our second requirement include business as usual as well as disasters. In flood modeling, we do a lot of design storm type analysis where we're just looking at one storm. We said let's look over a long time frame here. And the third requirement here include disasters that are representative of climate change. Of course, we want that in there. Um, and the fourth one, let's allow for addition of proposed strategies. So this might be one of the best parts of the tool, is that if you're planning on elevating a seawall or adding some other adaptation or mitigation measure, you can do so within the tool and see what the effective benefits and costs will be. Include a long enough timeline to measure return on investment. So we typically do these things over what we call a planning timeline, which is a 30 to 40 year timeline. So we're going from present day out to 2050, 2060, that kind of thing. And then finally, let's make all this conductable in a planning context. So in other words, 12 months time frame, 6 to 12 months for a community, and $100 to $200,000. This is what communities typically spend on their master planning efforts. Let's make it possible to actually do this study within that amount of time. So what we came up with is City Simulator. It is an Esri ArcMap extension. So it runs within, everyone's familiar with, Esri's ArcMap GIS tool. It just plugs right into that. And you can use all your GIS data. If you're processing data with GIS tools, they're all there. And so it makes it quite easy to sort of continue working in your normal workflows and use City Simulator at the same time. Um, the idea behind it was, first you build a digital twin. That's on the left side of this slide. And we wanted to get very detailed with it. So we said, let's include system users. So this is it's called an agent-based model. which means that if it's a population of 1 million people in your city, we have an avatar population in the tool of 1 million people all moving around the city, so that we can measure, how they're disrupted when climate change events occur. Um, we have system infrastructure, so this includes all the parcels, buildings, roads and rail, stormwater, wastewater, all the utilities, and the natural systems, rivers, soils, and so on. And then we also have system control. So how does a community typically control their system? It's through stuff like political boundaries, zoning, building codes, and so on. All of that has to be in our digital twin as well. In the middle of the chart, when you see simulate scenario, once we have our digital twin together, this is what we do. Um, it's called a nested loop algorithm. And on the outer loop, it runs once a year. That's really sort of for simulating urbanization as it occurs. So if you start with, economy up at the top there, um, and a rate of improvement of the economy gives way to new commercial buildings. So if the economy is really strong, more commercial buildings are added to the landscape. Those commercial buildings have businesses in them within the simulation, so that adds new workers. And those new workers, they have families, so we add their families, and they need new residential property, so we add that to the landscape too. Um, we then add new infrastructure, so all the utilities, roads, and so on. And then we, assess how this impacts the city. So floodplain adjustments for new development, ecosystem impacts, and carbon footprint. In the center, that's a loop that runs once a day, and it starts out with a forecast of storms. Daily forecast going out 30 years, um, and that forecast is built with global climate models, and that's how we kind of get the climate change signal in there. So if the global models are predicting increased rainfall, larger storms, more frequent storms, and so on, that's included in that forecast. Every time a storm occurs, we assess which buildings, which infrastructure are impacted, and how much, and how long are they going to take to recover, and what it's going to cost to recover them. And then we simulate them recovering over, day after day, as long as as long as we estimate it'll take them to recover. Um, while that's happening, the buildings aren't operational, roads are flooded, and so on. We assess the disruption to the agents in the system. Who's not getting to work, who's having to take a longer route to get to work, and so on. Also within the daily loop, we're simulating travel, people moving through the city. We're simulating work, people going to work, and commerce and other activities like that. On the right side of the chart, you can see what we're doing as we do the simulation is evaluating key performance metrics. And these focus on the triple bottom line of economy, people, and environment. So we're measuring, specific metrics like how many people were disrupted from going to work, um, how many people are impacted by heat exposure, how much storm damage is occurring, what is when we're adding in adaptation and mitigation, what's the return on investment of doing those, and so on. In an environment, we're evaluating carbon footprint both for buildings and for vehicles, pollutant loadings and streams, and so on. This is just a partial list. There's actually a lot of metrics that we evaluate. What does this all end up looking like? Here's some screenshots from a application in Fayetteville, North Carolina. We actually did this quite a while ago in 2017. This is actually, the red line is Cumberland County, and you can see the parcels in here and so on. In fact, the next slide kind of zooms into part of the city. And so you can see the detail that's in the model. There's all the parcels. There is, all of the road network. These roads are colored according to congestion. We're actually modeling the, people traveling from home to work and so on. So we can evaluate congestion levels on the roads. If I go to the next slide here, I've actually selected a building within that image. And we can see we actually get, each building has a lot of information associated with it. I mentioned in the beginning, one of our requirements was to make this possible to do within a 12-month time frame. If we had to create flood models for the whole community, that would strip us way past our 12-month time frame and take away our budget. It's an expensive process. So what we actually do is use existing flood models like FEMA NFHL models or any other models that are available for the area, and we bring them into the tool. Like we sample the model's estimate of flooding depth at each building and at each road and so on. So we get curves like this. These are called rain to flood response curves. And so you can see there's actually two curves on here. On the x-axis, this is sort of the size of the storm that occurs. So if the climate models are predicting like a 5.5-inch storm, we can get the level of flooding that happens at this building as a result. We also have curves that are called depth damage curves from FEMA's HAZUS program. And these give us, for the flood depth that occurs, which we get from the y-axis here, we get the percentage of the replacement cost of the building that is required to, fix the damage that occurs from the flood. So we can go all the way from, this global climate change model forecast of a rainfall event to building by building estimates of storm damage in terms of dollars every time a storm occurs. And that's how the simulation works. This is just an example. So let's say a 5.5-inch storm occurs. We can see we get 1.55 feet of flooding in the house, in this particular house. We go over to this chart, 1.55 feet equates to about 6% of the replacement cost of the house. If we estimate that at $300,000, then it's an $18,000 storm damage for this particular house. And again, City Simulator is simulating every building in the city, every road, and so on. So we're doing a lot of estimates of damage like this during a simulation. Here is a kind of a result that comes out of having all that data. The highlighted line that you're seeing here of roads within Fayetteville, they're related to this one building that's selected in the center. It's a commercial building. The tool has information on who works in a building and where they live within the city. And so what it's able to do is to work out their commute path every day. And so for every commercial building we have, we can click on the building and figure out which roads essentially support people getting to that building and being productive every day. Um, if the next slide shows, this is sort of just popping up some information related to that building. It shows you all the employees. These again are just agents within the tool. These aren't actual real people, and it's just sort of a statistical representation of the population. But each agent here has a commute path. So these numbers are indexes of the roads, segments of roads that are taken by that person to get to work every day. And because we have that information, we have a powerful way of understanding, when events occur, which parts of the city are impacted, and we can quantify that impact. We could do the same thing for stormwater assets as well. Here you can see I've circled a culvert right here. There's a road going over it. And so if I move forward here, you can see this is called an overtopping curve, which is similar to the rain to flood curves we saw for the buildings, except now this is giving, for a certain size of storm, it's giving how much is the road here in this particular culvert. You can see the picture of it up on the left there. How much is it overtopped by flooding? This is really important because, as that depth increases, um, the force of the water on the culvert will likely damage the road entirely and sometimes sweep it away. And then you're looking at 3 months, 6 months of not having that road as the replacement is made. That has a huge disruption on a city's daily commute patterns and productivity. Similar to the commute footprint for the building, this selected set of lines on the map, this is the road segments that are impacted by that culvert. If that culvert is damaged and disabled, that this section of the road network includes all people who travel over that culvert every day. And so you can see there's a widespread impact from having that culvert taken out of the system. When the tool actually simulates, you can see this is a screenshot of City Simulator. It's the Esri ArcMap program. If you use GIS, this should look familiar to you. And as you can see, it plugs in as a tool on the left side of the screen here. When it's running, it actually simulates the map, simulates the storm happening. So normally I'd have a video of this, but I've had to do screenshots here. And what you can see here is on the left side of the screen, the chart that you see, the red line is the forecasted rainfall. So you can see there's a storm that's about to happen here. That's a 12-inch of rainfall storm in 24 hours. That's a big storm in Fayetteville, on the level of something like Hurricane Matthew, which happened there in 2017. Um, and the green line that you're seeing there, that's the engaged workforce. So that's the number of people. Its axis is on the right side, so it's saying 96,000 or so people are working, on a daily basis within the city. So when the storm actually occurs, what you can see is there's a drop off in the engaged workforce, and that's because the people who live or work in the buildings that are highlighted on the map, you see the black dots, they're not able to get to work, and so productivity or engagement drops as a result of that. Again, I'd show this in a video, but typically we're running this type of simulation for 30, 40 years. And so we get 30 or 40 years of this activity, this sort of disruption, and can really start to understand what level of disruption it has on the city in the long term. Um, what do we do in the end with all this information? We will typically do scenario analyses. So we'll look at, you know, a baseline run where we don't put any mitigation or adaptation into the city at all, and see what level of vulnerability the city has. And then we'll create scenarios where we add adaptation and mitigation. And this diagram sort of illustrates two of them that we did to compare. um, the green boxes that you see, those are, the adaptation measures that we tried. The orange boxes are the costs for them, and the blue boxes are the resulting benefits. So in Fayetteville, a big problem was flooding in the floodplain, buildings in the floodplain, and then dam breach. There's about 30 dams across the county were breached as a result of this storm that occurred, Hurricane Matthew. Um, and that's a huge number of dams. A large number of sort of lakefront homes were impacted as a result of it. So we said, okay, what if we had all the money in the world in this first scenario, and we could acquire all land in the 500-year floodplain, and just remove the buildings from the 500-year floodplain, thereby avoiding flood damage entirely, at least within that area. And then what if we can reconstruct all of the breached dams in the way they were built, which is typically earth and fill? That would end up costing them $315 million, and the dam reconstruction would be 27 million. So about $342 million, way more than city of Fayetteville would ever have in order to do this kind of work. The benefits they would get from it, though, would be, the city simulator estimated $9.3 million a year in city productivity, um, would be, or loss of that productivity would be avoided. Flood loss is avoided. So this is damage to buildings is $8.8 million per year. And remember, this is over a 30-year time frame. So that's a big number. And then in terms of dam breach, real estate values lost, avoided would be $4.2 million. And tax revenue would increase 2%. City simulators calculating all those different metrics. The city said, well, we probably would never be able to get this level of funding. So we said, okay, what can you do with the level of funding you could reasonably get? And so in this second scenario, we said, let's acquire only flooded land during Hurricane Matthew. So if it's a storm up to Hurricane Matthew size, um, there won't be any flooding in those particular spots. We don't acquire all the land, just the land that was damaged in Hurricane Matthew, and that cuts our price tag down to $55 million. For reconstruction of the dams, we said, well, let's let's actually spend more and reconstruct the dams with hardened, concrete, so that when storms occur in the future, they won't get breached again. And as a result of that, you can see the cost is actually lower, and that's because in this first scenario, we had to really, we had to reconstruct the dams every time a large storm came along. So you've actually saved money. The end result is you don't get as high a benefit. Here we get $6.6 million in loss in productivity loss avoided, and 4.9. You can compare these to 8.8 and 9.3. But in reality, you get 70% of the benefit of this first very expensive scenario at just about 16% of the cost. So, a helpful analysis. City Simulator has been applied now since that was one of our first exercises in North Carolina, emergency management. We've applied it now in many other locations, and it has gotten a lot of attention in the New York Times, Forbes, ESRI Science of Where podcasts, and things like that. And I'm going to go through a couple more of these examples just so we can see how we use simulation to investigate resilience. First, I'll do Boulder County. We did an assessment there, Boulder County, Colorado. We did an assessment of their resilience and vulnerability. We looked at they had 113,000 buildings in the county. They were included in the model. The entire road network, all 325,000 people, it was all, within this model. One of the most helpful results that came out of that analysis was this map that you see on the left here. It shows the level of average annual trips disrupted at each of the culverts and bridges in the county. There's about 200 of them. Um, what Boulder did was they went and actually what you can see on the chart in the right is that the green bars are much bigger than the blue and red. um, the different bars account for whether the flooding that was impacting a person was at their home, at their workplace, or on the road network in between. And because the green bars relate to the road network, you can see that's really where a lot of this disruption comes from, is flooding of the road network. Um, and what Boulder did, they submitted this result, and as an exhibit in a grant application to FEMA to get 3 of their bridges redesigned and rebuilt. And they were successful in that application because of evidence like this, and they are now in the process of doing that redesign and rebuild. The next study I wanted to look at is Hollywood, Florida. Um, this is a town that's just north of Miami, and the Atlantic Ocean is on the right here. You can see the black dots here, similar to the Fayetteville study. So, we're simulating, in this case, it's on the coast, though. So, we're simulating mainly storm surge and, tropical storms and things like that. That's the kind of event we're looking at here. Um, the thing I wanted to point out, a couple of things I wanted to point out about this is you'll see another chart on the left here. That's showing annual metrics. So that chart gives us the green box here is the amount of storm damage that occurs in this first year of storm. And the purple box is the amount of productivity loss. The take home here is that productivity loss is a big number, and should be considered when considering the benefits of adaptation and mitigation measures. The other thing I wanted to point out is these blue lines on the coast here. We actually simulate tidal levels in City Simulator when we do coastal communities, and we include a sea level rise signal in the tide forecasts. So what we're able to do on a road by road basis is understand how often is that road going to get impacted by what they call sunny day flooding. Um, and start to measure what is the impact of that. We have every building, every business modeled, so we can understand what is the commerce impact of something like a dry cleaner who's the road right outside the dry cleaner is getting flooded more and more frequently in the future. What is the impact to their commerce as a result, and what would be the benefit of like elevating the road or doing some sort of measure that would reduce the impact from that sunny day flooding. The third one I wanted to talk about is the Port of Prince Rupert. This is a sister tool we created called Seaport Simulator. It uses the same simulation idea to investigate resilience, but in this case, we're looking at cargo flows going through a port. We built a digital twin of the port, including, we did a LiDAR flight, built 3D buildings of, 3D structures within GIS of every building, every dock, every road, every rail, all that information is in there. So as sea level rises, we can actually understand which parts of the workflow going on at the port, the operations at the port, which ones are being impacted and to what degree. But we said, really what we need to be thinking about is the full global supply chain when we do this simulation. And so you can see, for something coming through the port of Prince Rupert here in Canada, we need to consider ships leaving from places like the port of Hong Kong, going through tropical cyclones in the Pacific, um, being interfered by sea level rise, as I mentioned, rail blockages from freshet, that's the springtime flooding from rivers in this area, um, extreme cold and extreme heat as the rail moves across the continent. That can cause slowdowns, both cold and hot temperature slowdowns, and rail blockages from things like atmospheric river induced landslides. So all of these are climate change influenced parameters, and they all affect the global supply chain. And so the city seaport simulator simulates all of this, and this slide right here shows what it looks like within the tool. You can see we actually make a forecast of tropical cyclones going out 40 years, a forecast of sea level rise, a forecast of rail blockages from things like landslides, and a forecast as a result of all of this, a forecast of TEUs, which is 20-foot equivalent units. That's sort of how you measure cargo flow, container flow moving through the port. And so you can see as these forecasts blip here, there's a rail blockage, there's tropical cyclones, and so on. As the sea level gets too high and prevents um, operations at the port, we see drops in the process TEUs because operations stop when these types of events occur. In the end, what we're able to do, and again, this animates, so you can see this chart built over the course of the simulation. What we do is we measure, the yellow bars here are what if there were no climate change stressors at all. So that's sort of our potential amount of cargo that can flow. And the brown bars are what if we add in all of these stressors. And so you can see there's a difference between the brown and yellow. And really the name of the game here is to measure how much of a difference there is and what can we do to reduce that difference over time. The port is this project's ongoing and should be done in the spring. And the port's gotten a lot of good information from this study that they're now turning into mitigation and adaptation measures. One final thing I wanted to go through here is epidemic simulation. When COVID first started up in spring of 2020, it occurred to us, hey, we're already simulating agents moving through a city, we're simulating buildings, we're simulating people going to work, and so on. So we could actually very quickly stand up an epidemic model, which we can then make available in addition to the other types of simulation that go on in the tool. So we created an epidemic module, and we based it on the SIR models, which we saw a lot of as COVID took hold in 2020. SIR, it's sort of a way of modeling buckets of people. S is susceptible, I is infectious, R is recovered. So people move from being susceptible, then getting the disease and being infected, and then recovering, and they move to the R bucket. And so what we can see here is these are results that came out of the model. The adaptation and mitigation solutions we tried for epidemics are, you'll be familiar with them, things like social distancing, vaccines, and so on. And one of the first ones we tried was social distancing. And so you can see what the difference here is. Like the blue line that you're looking at, that is the number of people infected. So you can see it just jumps dramatically when no one's social distancing, no one's vaccinated, and then everyone recovers. Um, Whereas with highly compliant social distancing, we found that you get these waves of infection, but they don't sort of stop the city altogether. They're much more manageable. The green line here is engaged workforce, just like the other charts that we saw. So this was a really interesting result, and really illustrated the power of having this simulation framework that we can investigate other phenomena with. One of the really helpful studies we did, once we got this module going, was what if you have an epidemic going at the same time that you have a hurricane happening? And we got findings like, your shelters, your hurricane shelters, are going to have to be much bigger if you want to maintain social distancing while recovering, from a hurricane, while sheltering people, and also having COVID going at the same time. So really, really kind of interesting results from that analysis. Um, Here is again, it's a GIS based tool. So what we did in this initial run here was we actually created a virtual town. So that's why our town here it is actually in a map, but it's just this sort of square area. And we have, if you look at the image down at the bottom there, you can see roads moving through the town. You can see those are blocks basically. And comparing the two images there, you can see, blue basically means, a building that has infected people in it. So, the upper simulation, when there was no social distancing, we just saw this massive wave hit the town and sort of disable the whole town for a few weeks. Whereas the one below, you can see there is still infection, but it's managed and people can get around and work, even though the infection is happening. Future directions for City Simulator and Seaport Simulator. Um, we are expanding in lots of directions. There's deeper neighborhood and behavior modeling. So we're getting into more detail to understand how activities like commerce are impacted. Um, there is smart city technology. There's a lot of smart parking, electric vehicles, and so on that people are proposing and prototyping that they want to try out in the simulator to see what impact they really have on a large scale. City Simulator Online, as I mentioned, it's an ArcMap tool now, but we actually have a prototype online tool where you wouldn't need to have GIS software. You can just use it as a web app. um, Interactive scenario development. We would, like to get to the point we actually do workshops now with City Simulator, but typically the analysis has been done beforehand. We would like to get to a place where we're proposing new adaptation measures in a workshop and running them, in the workshop in real time. That would be great. So we're working on that. Um, Regional and transportation corridor assessments. Like I talked a lot about cities, but this simulation idea can be applied to whole regions, to transportation corridors. We're currently doing in North Carolina the US 74 highway, 200 miles of highway, 10-mile buffer on either side. And we're about to start doing the I-87 corridor as well. So those sorts of analyses, we're learning simulation really helps out with those too. Um, a national database of community digital twins. There is a bit of work to put together these digital twins in City Simulator. So we're saying, maybe we could do the work up front and sort of create databases of this information to make it easier to do a fast city simulator exercise. You just use data that's already been created. And then finally, uncertainty estimation. We're improving our techniques there. Um, all of this forecasting stuff we do, it's all uncertain. And communities are typically interested in what is the worst case scenario, what's the best case, what's the medium case. And as a result of that, we have to have simulation techniques that estimate those things, those different metrics. And so we're adding to those on a regular basis as well. Okay, I think that's about it for the presentation. I have a link here to the landing page for City Simulator if you're interested, and also my email if you want to contact me with any questions. And I can take any questions at this point.
Hi, Steve. This is Karen. Thank you so much. That was a great presentation. Um, I think Regina might be having maybe some audio issues. But we do have a couple questions. Um, our first question comes from Lawrence Frank, and he's asking, how do you see the use of City Simulator for military installations?
Yeah, yeah, really good question. We actually recently, developed a plan to create a installation simulator tool. Um, and the idea behind it was it would be similar to City Simulator in the sense that we would simulate the installation and then all of the supporting housing and population around the installation. But really, the operation simulation would be focused on things like operating runways, and really sort of simulating the mission that takes place at the installation. So we went pretty far with sort of conceptualizing what that tool would be, and we're exploring options for creating that tool now.
Great. We have sort of a follow-up question to that one. Um, where to go from Roland Guzman. He's asking, building on the previous question, do you have any thoughts about how military bases can work with their local municipal partners to use the city simulator?
Yeah, yeah. They are doing in places like um, Virginia Beach, that area. They do joint. I think they call them JLUCEs, but it's joint planning exercises with military personnel for the military installation, and then town planners and state level folks as well. And I think the academic community there is also participating, and they're really looking at if we have to solve the resilience problem from the perspective of the military collaborating with those local institutions, how do we do that? And so, I would see a tool like installation simulator, for example, being a perfect tool for that group of people to use. Typically, the analyses we're doing, they're stakeholder based exercises, and they will bring in people from multiple institutions. So it would be a similar process.
Great. Thank you. We have a few more questions. Which component of the simulator is the most difficult to determine? It's a two-part question. And do you engage a stakeholder group when formulating the parameters that are locally driven?
Okay, great question. I'll do the second one first. As I just mentioned, yeah, we definitely include stakeholders. There's really no point in doing these exercises if the stakeholders aren't included as part of the process, because the point of this exercise is to bring clarity to what the impacts will be and what the return on investment will be. But really, what we want in the end is action taken, and the mitigation and adaptation solutions we look at, things like elevating buildings, acquiring buildings, and so on, we want those to actually happen. So including stakeholders in the whole process is really necessary. And yeah, we do committee meetings with stakeholders where we go through not just the results of the analysis, but what assumptions are we making in the analysis as we do it, and they have full transparency into that as well. So it's not a black box to them. They see what analysis we do, and have a role in determining whether it seems reasonable or not, what the parameters are. um, the first question, what component of simulation is most difficult? I always answer to that. It's easy to model floods and climate change and things like that. it's difficult to model what people will do as a result of it. Some of the modeling we do with sea level rise is, are people going to make a decision to actually leave the community and go somewhere else? If you have a coastal um, property, a home or something like that, and you're looking at it flooding, you know, from twice a year right now to 200 times a year 20 years from now, what decision do you make? It's difficult to actually simulate what decision you would make there, what a decision a person would make there, and get that right. So that's definitely the difficult part.
Great. Okay, we have a question from Kwang Hui. Um, what have been the largest obstacles or challenges in performing accurate and useful simulations?
Yeah, good question. One is just sort of volume of data. There's a lot of data that goes into these models. Where like one simulation of North Carolina's uh, US 74 corridor I mentioned earlier. I mean, I think we're over 100 gigs of models that are being pulled to do that analysis. So it's a lot of information, and then of course it's different models with different data structures measuring different parameters. So just kind of harnessing all of that and doing an analysis with it, that's a challenge. Um, but of course, the other challenges are, what questions do you want to answer with your simulation? Getting everybody in agreement on what assessment you're actually going to do. That's a stakeholder exercise, and we will obviously make suggestions as Atkins, but we really want to have you know um, collaboration there in terms of what's to be modeled. Very often stakeholders will suggest metrics during our workshops that we hadn't even thought of, and turn out to be very good indicators that move the needle in the end in terms of taking action. Again, with this North Carolina one, that's the one that's most recent. They said, well, let's put in a metric that measures, what metric tons of freight are disrupted on trucks and rail as a result of future storms along the corridor. We were doing disrupted trips, but not like freight itself. So that's an example of a collaborative effort that ended with a metric that's actually much more relevant and important to them.
Great. Um, I'm going to skip around the questions a little bit because this one sort of goes along, I think, with the part about the data. Um, and what sources of data do you use to enter into the physical models?
Okay, yeah. Um, for We have flood modeling, and for that we will use things like FEMA flood models, the ones that make up the National Flood Insurance Program modeling, and that's typically HEC-RAS. We also there's a lot of 2D modeling of rainfall influence flood right now. Pluvial modeling will include those. At the coast, we use things like AdCirc models to model storm surge from hurricanes and things like that. So that's all within the flood modeling realm. Within the travel modeling, there's a model called TransCAD that a lot of the municipal planning organizations use. So we have tools that import results from those models. We use census data, measures of population, number of jobs, number of households, commute times they're all reported in the census, and we use that information to calibrate, where we put agents in our system. Those are just the big ones. We usually have a lot of other sort of either models themselves or other reports that find conclusions that we try to calibrate to in the process.
And to follow up on that question, Raymond asked, is the tool used more for planning and emergency disaster planning, or are you using it for, other um, applications?
Yeah, the original purpose of it was for planning, master planning. We are getting into a little bit of the high detailed emergency response simulation. So what happens in the 5 days after a storm, that kind of thing. And as I mentioned, the seaport simulator, we're simulating global supply chains there, but it's still more of a planning purpose to do the modeling, so that we can know kind of upfront, if we take these actions, what return on investment are we likely to get. Typically, after you do a city simulator analysis, you're going to then go move to um, a full detailed design of something, whether it's elevating homes or building new infrastructure and so on, and then go on to constructing it. So we're really kind of at the front end of the process, and at the planning step.
Okay. I have another question from Roland. Oh, wait. No, another question from Roland. How many cities around the country would you guess have digital twins already created? And then he goes on to ask, comment that he imagines that not a lot of cities have made that investment required yet to build that digital twin.
Yeah, that's kind of a nuanced question. There are, like, the data sets that I mentioned, things like parcels, building footprints, roads, rivers, and so on. Those are for the most part already existing, and in many times it's not the city that's maintaining them. It'll be either state level, maybe county level, or even federal level databases. So, what we've been able to do is, within City Simulator, is we tap into APIs that are being served with those databases information, and it makes the process of pulling all that data and making a city simulator digital twin much faster than it used to be. 10 years ago, it would be weeks and weeks of collecting data to try to do it. Um, Many counties out there, they have a tax assessor database already. Like, that's how they get their tax funding. So we can often use that as the building blocks of the digital twin. um, Having an actual digital twin in existence already, many cities do not have that. I would agree with that. um, but the bigger ones, the more progressive ones in terms of technology, they often do, and we can make use of that information too.
Great. So we just have a couple more questions right now. Well, Jay says, what a great presentation you've given. Have you used the simulation to model impacts of cascading failures?
um, yeah. I guess I'd need to know exactly what he means by cascading failures, but you know, within the city simulator, it's we're modeling things at sort of an atomic level. Like, if someone can't get to work, then they take this action, and if they take this action, then maybe another action happens as a result. So that's sort of all embedded within the city simulator modeling. Um, so I guess we are, by nature of, we say, the way we set up the simulation, cascading failures are included. But I guess I'd need to know, if Jay has something specific in mind there.
Okay. So Jay, if you heard that, if you want to elaborate a little bit more, we should have time to get back to that. And we also have a question from Steph Harrison. When you quantify disruption from a disaster, have you incorporated any socioeconomic indicators to understand disproportionate impacts to certain populations?
Yeah, that's a great question. We're doing that. We did that in the Boulder example, and we're doing it in the North Carolina to US 74 example. Um, and the way it's sort of taken shape at this point is, we are looking at, the census data will break down by census block group, poverty levels, minority, in terms of race, those sorts of metrics. And so what we can do is, we measured the disruption for each of those census block groups, and then the ones that fall into those sort of categories, those disadvantaged population categories, we could look at their results compared to the general results. And so that's typically the way that we're doing that now. Um, I think that we largely think we need to go into more detail in that, because the census block group can quite often have, um, you know, populations that are in poverty, and also populations that are definitely not in poverty. So we might not be going to the level of detail that we would like at this point. So that's definitely an area of expansion within the modeling.
Great, thank you. It doesn't look like we have any more questions, but there's just some great questions and a lot of great Q&A we had there. Oh, wait, Jay popped back up. He said by cascading, he was referring to the impact of loss of one type of critical infrastructure on another type. For example, flooding leading to power loss impacting transportation.
Okay, I get it. We're definitely looking at, flooding impacting transportation directly. So when, roads are overtopped and so on. We're also looking at flooding impacting power. So an example we did in South Florida, for example, looked at, where are the main power transmission, and where is that infrastructure, and which neighborhoods does it serve? You know, and so we were able to say, okay, if that transmission goes down, which buildings are impacted as a result? So that was included in the simulation. And when those buildings didn't have power, particularly their commercial building, we made an assumption that people couldn't get to work. So we would see impacts like lost productivity as a result of power loss. Um, in terms of how they all relate together, again, I think I'd go back to we've set the city simulator up in such a way that people are making decisions on a person by person basis, and those decisions are impacted by how hot is it going to be today, do I have power, is my building flooded, and so on. And I think the nature of making the decision process at the person level means that we're necessarily modeling the cascading effects of these types of disasters.
Great, thank you. Well, I guess if there's no more questions, it's almost 1 o'clock. I want to thank you, Steve, for taking time to present today. It was really interesting. Um, and I want to thank all of our attendees for joining us today. And we hope to see you at a future webinar or SAME event.
Thanks, Karen. It was a pleasure.
Thanks. Bye-bye.
Bye.